Just because a number divides the order of a group does not mean there's a subgroup of that order. Simplest example is in the group A4. What's that? That's the alternating group on 4 elements, right? Permutation group. Even permutations that can be written as a product of an even number of 2 cycles on the set 1, 2, 3, 4. How many elements does that have? It's got order 12, right? Because S4 has order 4 factorial, 24. A4 being even permutations has half that order, because S4 also has the same number of odd permutations in it. 4 factorial divided by 2 is 12. But the claim is that has no subgroups order 6, even though 6 divides 12. To verify this, recall, first of all, that A4 has 8 elements of order 3. If I asked you to verify with a calculation, so to speak, that A4 has 8 elements of order 3, you should be able to do that. What would the elements of order 3 look like? They would be 3 cycles, A1, A2, A3. By the way, such a 3 cycle, even though it's got 3 elements in it, and its order is 3, it is an even permutation, because you can write it as an even number of 2 cycles through that trick. This 3 cycle can be written as a product of 2 2 cycles, and they're not disjoint 2 cycles. They both have A1 in common. Does work. A1 gets mapped to A2 there, and A2 stays fixed. So ultimately, A1 gets mapped to A2. A2 gets mapped to A1, which gets mapped back to A3, matching the fact that here we see A2 getting mapped to A3. A3 stays fixed, then gets mapped to A1, just like in this notation, we see A3 getting mapped back to A1. An arbitrary 3 cycle can be written as a product of 2 cycles. It is an even permutation. How many possible choices are there for A1, A2, and A3? 4 times 3 times 2. But then I have to divide that by 3. Why? Because there are 3 different ways to write this 3 cycle. That's one way. Here's another way. And here's a third way. Giving me altogether 8 such permutations. You could also list them out. 1, 2, 3 would be one example, etc. You'd see you'd have 8 of them. A4 has 8 elements of order 3. Suppose, for the sake of getting a contradiction, evidently, H is a subgroup of order 6. The claim is that there's no subgroup of order 6. So for the sake of getting a contradiction, the author doesn't say that there, but that's the assumption, is this is a proof by contradiction. Assume to the contrary that H is a subgroup of order 6. You want to get a contradiction out of this. 2 things that can't possibly be true at the same time. What are the details? Let A be an element of order 3 in A4. There are 8 such elements. Pick one of them. If A is not an H, then this is true, first of all. Where does that come from? If A is not in H, then A4 is the union of H and this left coset. H is a subgroup of A4. We're assuming it's got order 2. A4 we know has order 12. That would mean the index of H in A4. Oops. H has order 6, sorry. The index of H in A4 would be 12 divided by 6 would be 2. There would be 2 distinct left cosets. And we know that if A is not an H, which is what we're assuming here, then AH would be different than H. This is going to be a distinct left coset from H. These are 2 distinct left cosets, and there can only be 2 of them. That's enough to say the union of those 2 is all of A4, and they would also be disjoint. But then A squared is an H or A squared is an AH. One of those 2 things has to be true because A squared is an element of A4. Both of those assumptions are going to lead to contradictions. If A squared is an H, then so is it squared by closure, right? H is a subgroup. If I assume A squared is in H, then A squared is going to be in H. But because A has order 3, that's the same as A. Because A cubed would be E. Which would mean what? Which would mean A is in H. That's a contradiction because I assumed A is not in H. On the other hand, if A squared is in AH, what does that mean? It means A squared equals A times H for some H and H because of what it means. This notation means, right? That's the set of all elements of the form A times H as H varies over capital H. But that also implies A is in H. Why? Cancel, left cancel. A squared equaling AH would mean A equals H. Also a contradiction. The only thing that must be wrong then is that our assumption that H has order 6 must be a faulty assumption. It's a contradiction. So it could, because it's saying that any subgroup of A4 of order 6 must contain all 8 elements of order 3, which is absurd. That's the final contradiction.